Fine. Thank you. Good morning, everybody. It's an honor and a pleasure to talk to you a little bit about the experiment I'm working on after the name Programmable Quantum Simulator with Strontium Rydber atoms in optical tweezers array. I'm Andrea Fantini. I'm PhD student from University of Florence. So basically, our goal is to create a platform that is essentially an array of single atoms and make them interact and study the dynamics and all the interaction we can create easily. The idea is to exploit the new state-of-art optical techniques that allows us to address a single individual quantum objects. So what is the ideas behind this our purpose? Essentially, what we want to do is to combine the best features of two different worlds. On one hand, we have neutral atoms in optical lattices that are well known to be scalable up to a huge number of atoms. So we are talking already about mesoscopic system. And also they offer us the possibility to real-time rearrange the geometry. On the other hand, we have the ion trap world that is famous for its fast experimental cycles and excellent single atom control and detections. Before going further, I want to just give you a little taste of the motivation that are leading us towards our goals. So basically, when we talk about quantum simulations as us, or more in general, quantum computing, what we are meaning is that we can give a support to even a hybrid machine that is both classical and quantum, in the idea that blocks of algorithm can be accounted and run, if you want, by a specific quantum platform. So if I talk about quantum simulation as an analog, what I do is basically I map them in such a spin model. If I talk about a proper quantum computing or in general a digital quantum simulation, what I do is to find a way to mediate the interactions of the gates between specific techniques. In our case, it's the so-called Rydberg interaction. So this is basically our motivation to go further. Let's go further, and as every good recipe, we're gonna have a few ingredients. So Rydberg is one, strontium element is the other one, and optical tweezer is the first that we're gonna discuss now. What is an optical tweezer? An optical tweezer is simply a really tightly focused laser beam that will create a deep trapping potential. So we're talking about almost 1 micrometer waves for 1 millikelvin of depth. That means that with these techniques, we can trap single atoms directly from a normal cloud of cold atoms. That is basically a MOT. Of course, the MOT has to be at least on the millikelvin temperature, but with these techniques, we can right away trap and manipulate the single atom. But of course, as I said before, we don't want just one atom, we want an array of atoms. What it means that we're gonna need an array of tweezers. For such a purpose, before the high number aperture objective, we want to create an array of tweezers. This is made through two main techniques. We're gonna exploit both. One is the SLM, that is a special light modulators. It's practically a device to create through holographic techniques such of array. And the other one is the AOD, so acousto-optical deflectors. But so how effectively we can trap those atoms one by one? When I have my tweezer focalized, I try to make my MOT there. So the effect is basically that when the density is enough, I'm expecting atoms falling down inside the tweezer. Thanks to the light-assisted collision, I'm gonna pairwise lose them. That means that if the number of atoms trapped is paired, I'm gonna end up with 0 atom in the tweezer because they will escape 2 by 2. In the other case, if I have an odd number of atoms, I'm going to end up with 1. There are many other techniques that allows us to go kind of quasi-deterministic loading, but the deterministic loading is still far from the practical or useful. So we're going to go just with a filling fraction of 1/2. For this reason, we cannot have our final perfect defect-free array of atoms, but we don't want the first situation, we want the second one. So what's the solution? The solution is to apply an reordering, we call it. So basically, we gonna exploit both devices. The SLM will create a static trap. Whatever geometry I want, in whatever plane, even 3D, I can create thanks to the SLM, but I cannot create and produce this reordering phase thanks to the SLM. It's a little bit slow. It's way more useful to use AUD that will, as a tweezer, take the atom and move it from trap to trap. This is basically the idea. So when the reordering is done, I'm happy. And so these examples here are made just through AUD, but many others, geometry and so topologies can be achieved through these techniques. And so the key aspect of this platform is that it's scalable, because I create a huge number of traps. It's of course rearrangeable, even before or after the loading, and we hopefully it's defect-free. But most of all, it's interaction-free. Why so? Again, because we're using neutral atoms. So what are then the key aspects of this platform? Why is this good? So the main difference in respect to other traditional ultra-cold gas experiments is that, as I said, it's a mesoscopic system. So we're talking already about more than 100 atoms. In principle, we can account and reach any geometry that we would like to experiment, and offer a high repetition rate. That means that in a short time, we're gonna collect a really huge amount of data to make an all and consistent statistic on it. So the other two ingredients are, again, Rydber and strontium. Let's investigate a little bit of Rydber. Rydber atoms is essentially an atom that has been excited to a higher level, higher energetic level. So we're talking about like a principal number 100. In this case, the wave function of the electron moving around the nucleus will be displaced about 1 micrometer more. So what's the point in doing so? The displacement of the wave function will create interaction at long distances. So if I have like 2 atoms, I can in an easy way control the interaction between those. Essentially, the cool aspect about Rydberg excitation is that it's tightly dependent on the number of the excitation. So in this way, if I control the frequency I'm exciting the atom with, I'm controlling the strength and the distance of such interaction. I think the most interesting concept about Rydberg is the so-called Rydberg blockade phenomenon. that basically works like this. If I have my atom and I wanted to excite it to the Rydberg state, it's kind of easy, it's straightforward. But what happens if, like, let's try with two atoms? Of course, if they are long distance, they will not interact, so they're like a separate system. But if I put them next to each other, what happens is that basically the van der Waals interaction won't allow me to excite them both to the regular state. Essentially, what means that one can go high and the other one wrong. But of course, this is such a classical idea. In quantum, what we get is the superposition of the Rydberg excitation and the ground state. And this is kind of a useful and easy way to create entanglement and to control interaction. But so if it's true that I have such a behavior, it must be a threshold. The threshold in the distance is basically the so-called Rydberg blockade radius. That is, in fact, the distance for which two atoms will interact and no more be able to get excited both at the same time at Rydberg state. So where is the quantum simulation? For instance, if I take it like, for example, this is like a Hamiltonian, and I want to map this kind of system thanks to Rydberg. I can say, all right, the ground state is the spin down and the Rydberg is spin up. In this case, I can express my Hamiltonian as a transverse and longitudinal field of the due to the Rydberg excitation, and the last part would be the next neighbor column. In such a way, it has been already proved that it's a really useful technique, a way to approach the evolution from a disordered system to a magnetic ordered one. So we can easily see variating the range of the interaction, basically just understanding in this radius that we call the Rydberg blockade radius, how many atoms I am going to have in it. Or I can make the array thinner, or simply changing the excitation to have a bigger radius. In this case, I'm going to end up with an ordered system. And the interesting thing is what happens after I quench my interaction later. In this case, I'm going to follow how the Rydberg excitation will behavior in this evolution. So the next element is the next ingredient is strontium atoms. That is really handy for its electronic structure. Is an alkali earth atoms. That means that we have two valence electrons. Basically, strontium has 4 isotopes, but we are lucky because the bosonic isotope we use in the 88 is also the most common one. Maybe it's the other way around, since it's the most common, we chose that. It offers 2 main transition line. The blue one is the first step with which we cool down, and afterwards we will go with absorption and fluorescence imaging, and in intercombination transition in red, the thicker is essentially the cooling, the second stage cooling transition. But also, it is quite a good thing to have the clock transition over there. So, for all these reasons, strontium has been the best candidate to be our atom, and offers 2 different techniques to be cooled. One is the sideband resolved cooling, that is so much easier than a normal, with a normal alkaline element. And the other idea to cool them down, we are still evaluating these two techniques, is the so-called Sisyphus-like cooling. Let's remember Sisyphus was like this hero in Greek mythology. He was doomed by Hades to like roll this giant boulder up to on a steep hill again and again and again. So basically, our atom will do the same. It will get excited to another state that, thanks to the specific detuning, will be deeper. Will have a deeper potential in such a way with the oscillation when he'll eventually emits his photon, he will get colder. He's lost energy and it gets colder. So two different techniques, both good. But I think the most interesting fact about strontium is the way it can be excited to Rydberg state. And again, we have two different techniques. The first is the so-called two-photon excitation. Basically, I'm exciting off resonance on the 3p1 in such a way with the direct Rydberg excitation. I can go from 1s0, that it's going to be my ground state, to the Rydberg that I chose. And this is good because it reduces the scattering rate and heating. And in comparison to alkaline atoms, it is less needy of power, of higher power. The other one is kind of simple for some point of view, but the point is it's two-step excitation. That means that I have to bring my atom to the clock state, and afterwards I'm gonna excite it to Rydberg state. Well, on one hand, this is gonna be preferable because after I have all my atoms in the clock state, it's gonna be super consistent, and the excitation to Rydberg is gonna be way quicker. But the point is, first, it's a key feature of alkali earth atom, so it's gonna be like something special to do. But the point is, after this evolution and the study, want to understand what has happened, I still need to make an imaging on the blue transition. That means that I have to bring the atom back to 1s0. Just a quick overview on the experimental setup. So basically, the first part is the oven. It's a little bit tilted in such a way I can pull it and deflect in a collimate beam that reach the science chamber, where I put my objective, my coils, homemade somehow, and our cage of compensation coils. Basically, with this cooled coils, with water-cooled coils, we can reach a gradient of about 100 Gauss per centimeter. And if we want to exploit the clock transition and to control it the best, we need also Helmholtz disposition that will get up to almost 1000 Gauss. This is a quick overview of our experiment, and here we can see our spatial custom objective with a specific field of view. Of course, in principle, we could even think about having a better field of view, but in that case, we should put our objective in the vacuum, and this is not the case. I mainly worked on the lab script that is the work frame that controls the experiments, but I'm not going to worry you about it. This was our first blue mod. And essentially, what we are now is that the situation when we can run multiple shots, and now it's slowed down. And that is like just to give you a taste of what happens when you slowly turn on coils. Our latest results are blue and red mod that has been characterized in temperature and number of atoms. But the point is, what we want is not just a high number of atoms, but to have a good density. Why so? If I have like 5 times 10 to 11 atoms per centimeter square cubed, means that I have almost 1 atom per micrometer cube. That means I have almost 1 atom per tweezer, and this is like something that should be given. If I want now to see tweezers, I have to pass from absorption to fluorescence. Such a way I can finally see my 3 just found tweezers. And that's basically what we got so far. So to conclude and summarize, we chose the Strontium because it has a really handy electronic structure and allows us to use really easily and cool cooling and manipulated techniques. And also the cool aspect here is the high repetition rate. So we are able to make an entire simulation in inside one second. Basically, this is a platform that it's quite generical and also flexible. That means that can account 2 different words. One is going to be the quantum simulation for many body physics, like, as I said, quantum magnetism, out of equilibrium dynamics, and so forth. And on the other hand, quantum technology-oriented applications. So that can be optimization and annealing, as I said, with the hybrid machine, and also have can, in principle, give a good help to quantum metrology, thanks to the nice bulk state. This is practically it. I'm going to present to you my group from the right side. Vladisar Bradisev, Veronica Giardini, Jacopo Catani, me, Professor Leonardo Follani, Giacomo Cappellini, Luca Guariento, and Sean Storm. I thank you very much for the kind welcome and attention. It's not here.
I think it's here.
A couple of quick questions.
You talked a little bit about this with regards to the quantum magnetism, and you mentioned also at the end the flexibility. I guess I was just curious that, like, once you have this thing working, you know, what's your first fruit that you're going to pick off of the science tree? Like, what's the first thing that you guys are going to try to do?
Basically, we're going to start with basic easing models, going further with topological mainly, and so basically easing and Heisenberg models, they're going to be the first to be explored and studied.
Yeah, ask the next speaker ready to come to the front. Any more questions? And let's thank the speaker.
Thank you.